Hello all, welcome to the presentation on Embedded Boundary Scan. Myself, VARUN PULIGILLA. I'm a Technology Enablement Engineer from Tessent. In this video, I'm going to give some introduction on hierarchical designs, and then we'll move on to the description of boundary scan, embedded boundary scan. In addition to that, we'll also go through the implementation flow and observe the schematics to get a better understanding. Coming to the introduction part. As we know, different manufacturing industries create their IPs based on their own design constraints and many more things. At some point when we try to integrate all these IPs onto a single motherboard, or nowadays we squeeze different chips to form a single chip. Now these chips inside a chip are called as cores. So in order to design and implement these kind of larger amount of circuitry, it takes huge amount of time. If we talk about the DFT perspective, to insert and generate the patterns for the full flat design later in the design flow, it takes much more time. But if we go with a hierarchical approach, we can generate the patterns in respective levels of a hierarchy, like hierarchical design has physical level, subblock level, or the top level. We can generate the patterns at respective level, and we can reuse those patterns to map to the top level. That's the advantage of hierarchical designs. So now when we integrate different types of IPs, we need to maintain some standardization. So this is the point where we need something called as boundary scan. So what is boundary scan? As you can see here, it can also be referred as IJTAG, Joint Test Action Group. It is a DFT technique that facilitates the testing of interconnected circuitry. It also helps to understand the characteristics of input-output cells in the design. So wherever we have the I/O cells in the design, a boundary scan cell is automatically placed by the Tessent tool. It also shortens the time required to develop the manufacturing test and diagnostics, as we can place the I/O cells in different levels and observe the functioning of the I/O pads. If you see the tab here in the design, this tab has 5 important pins like TDI, TDO, TMS, TCK, whereas TRST is a reset pin, which is an optional pin, because a tab also has a finite state machine, which has 4 bits, so it has 16 different states. So if we follow a specific mechanism, we can also activate the reset pin without a reset pin. That's the advantage. And these yellow highlighted registers are the mandatory registers in a tab controller, whereas device ID register is an optional register. That is basically used to identify the ID of an IP in a whole design. So this is about the boundary scan overview, and this is done at the top level. But if we go to the physical or subblock level, then what? That is embedded boundary scan. So with embedded boundary scan, I/O cells can be directly placed into the cores, which is closer to the logic what they serve. It also simplifies the signal routing and improves the timing. So, of course, if we place the I/O cells at the places what we want in the design, the boundary scan cells will also be generated automatically by the tool at those places. That is the advantage here. Coming to the implementation flow. This is the standard Tessent DFT insertion flow and standard Tessent pattern generation flow. The red boxes here are the main differences between these two flows, and the yellow box here is the important command in the insertion flow. We'll clearly observe in the coming slides. Here the set DFT specification command decides what kind of DFT should be inserted in the design. So in this video, we are talking about boundary scan. So we can see how is that done in the coming slides. Okay, so this is embedded boundary scan, which is done at the core level, like physical block or subblock level. If we observe the flow, these are the Tessent Shell commands. We set the context to DFT while the DFT insertion. We set the TSDB output directory, which is Tessent Shell database output directory. We set the respective libraries, read the libraries, and read the Verilog file. Here the current design would be the module top, like whatever module name we want. And the design level should be physical block or sub-block level in Embedded Boundary Scan. And the DFT specification requirements, what we were talking in the previous slide, that is a yellow box, that is the specification requirements. Here the boundary scan should be always on to insert the boundary scan. And at respective IO ports, what ports we want the boundary scan to be implemented, we can mention them here. And then here we can create the DFT specification, and then we can process the DFT specifications. After processing, we can find all those newly inserted DFT design, patterns, instruments, all these things in the Tessent Shell database output directory. It is important to make sure we have the TCT BScan file, because that can be used to map to the top level while we insert the boundary scan. Here you can see the test case, which is available in the circuits and solutions. You can always ask our application engineers to access this test case. Coming to the boundary scan here. So if you see, I have also given the difference between pattern generation and TFT insertion in the flow. Everything is same like embedded boundary scan, but the design level here is chip. That is the top level. And the difference between the patterns and the DFT insertion is like, here we create the TFT specifications, here we create pattern specifications. And in the DFT insertion, we read the Verilog file, the .v file, whereas in the pattern generation, we just read the design name, and then we can set the current design. And the patterns would be, the context would be patterns in the pattern generation, and in the DFT insertion, it's TFT. So this is about the Tessent Shell commands, how we used. Coming to the schematic diagrams, this is the boundary scan implementation, which is taken from the Tessent Visualizer. And this has TDI, TMS, the reset pin, TDO pin, and the TCK pin. These are the 5 main pins which have been connected to the tap here. This is the BScan interface. This is a logical group def file design exchange format file, which is created respective to different types of pins accordingly by the tool. This is the boundary scan implementation. Coming to the embedded boundary scan, this is also the screenshot from the Tessent Visualizer. So if you can see this highlighted block, this is the EBSCAN block, which is in physical level. That is also connected to the top level using the IJTAG interface here. And the respective def block is also created. This EB output, EB input, these are the functional pins of the embedded boundary scan. You can also see the TCK, TDI are also connected to the tab in this implementation, which has the physical block and the top level block. So this is how we can integrate the EBSCAN to the top level. Coming to the advantages, the proximity logic enhances the efficiency and speed of data transfer between the IO cells. Like the closer proximity, the higher the speed of data transfer. Like we can place the IO cells wherever we want in the physical level or the subblock level. So, and this kind of placement leads to cost savings, and also the area can be reduced with improved timing and signal routing. So this is all about the video. If you have any questions, you can raise them in the comment section. Thank you.